Okay, so we want to know the equation behind this fifth axiom. So we assume the property let P of n be such that P of 0 is true and P of the successor of n is true when P of n is true. So this is how the fifth axiom starts. Now, why will it say that P of n is true for all n? And the equation is simple. P of 0 is true. This is one of the things we have already assumed. Now, because P of 0 is true, in the second part of this hypothesis, you can take 0 in place of n. Then the hypothesis will tell you that P of the successor of 0 is true. That is, this is true. In other words, P of 1 is true. Now, once you have got P of 1 is true, you can then apply the hypothesis with n equal to 1. So this will give you that P of the successor of 1 is true. That is, P of 2 is true. And it will go like that. So intuitively you can see that the property Pn should be true for all natural numbers. This is the equation behind the fifth axiom. Okay, and you should understand that this is an equation which we believe to be true because we are considering the fifth axiom as an axiom. So we believe it is true, and as long as that belief is not contradicted, things will go smoothly if we base our mathematics on this axiom. I mean, on the other things also, but this axiom is a part of that belief system. Okay. Now, now, how does this axiom prevent this sort of things from happening? Okay, say someone said that the natural numbers contain half integers also. So to see why, we can sort of think of a statement like this: no natural number is a half integer. Now this statement itself is informal because we are using the term half integer. We don't know what half integers are yet, but at least from the point of view of discussing the things, from our prior knowledge, we can see that these are half integers and we don't want them to be natural numbers. So we somehow want the fifth axiom to take care of this, to help us get rid of this situation. So we now want to prove this informal statement using the fifth axiom. So in other words, we will use induction. So it can be proved like this. So first of all, you have to prove that this has to be proved for all natural numbers. So we start with 0. 0 is not a half integer. That is clear. Why? What is a half integer? A half integer is a natural number plus 0.5. See, I have had to use plus here. So that's why this is another reason this whole thing is informal, because to me plus is still not available. But just for the sake of seeing how this axiom will work for us. So 0 is not a half integer. So that means our statement, our claim is true for 0. Now if n is not a half integer, that means if n is one of these things, 1, 0, 1, 2, etc., then clearly the successor of n is also not a half integer. So by induction or by axiom 2.5, every natural number is not a half integer, or to say it more nicely, no natural number is a half integer. So that gives you an informal proof, which is not a genuine proof because of these undefined terms and addition and all the things involved, which we have not introduced yet. But it gives you an idea as to how the fifth axiom prevents these things from happening. Okay. Now this, regarding this proof by induction, there is a remark which you already know. In fact, induction is something which we have come across even before introducing this standard treatment of natural numbers, and we have used induction to prove some statements, some results before, some formulas that involve the natural numbers. But still, to treat the thing formally, there is a remark or proposition, I think. Yeah, there is a proposition. Okay, I should keep the numbering intact. So what is this? This is a proposition in the sense that it is a template for a result that can be proved by induction. So in general it looks like this. P of n is true for all natural numbers n. Okay, where P of n can be any property. So if we see a statement that looks like this, then it can be proved by induction. And the proof goes like this, which you already know, but for the sake of completeness, I am just showing it. It's rather a strategy for proof, or a general structure of how an induction proof looks. Show that P of 0 is true. Show that P of 0 is true. Then assume P of n is true for some natural number n, and show that P of the successor of n is true. Then that's it, that ends the induction. Then by axiom, or then by axiom 2.5, we are writing that here. In general, we will write then by induction, P of n is true for all natural numbers. And the proof is complete. So this is more or less the template in which the induction proofs go. Okay. Now this induction principle, the way we have presented it, this is our assumption, one of our assumptions, but this has some variants, and those variants will be proved in due time. There are some things which are like this. Backwards induction. We can do induction in the backwards direction also. Instead of going towards more and more successors, their successors, we can come back. Okay. This proves helpful sometimes. And we will see this in exercise 2 to 6. So these things will come. Then there is strong induction, I think. Yeah. In strong induction, the induction hypothesis is stronger than what we assume here. Namely, the assumption that P of the successor of n is true whenever Pn is true. Instead of that, we assume more strongly that this is true whenever P of m is true, where m varies from 0 to n. Okay, so that sort of thing we assume. That is also sometimes helpful in some situations, and that we will see in, that will be proposition 2 to 14. Okay, and there is one more, transfinite induction. It's a generalization of induction from the set of natural numbers to any well-ordered set. We will see what well-ordered sets are, and this is, we will come across this even later than these things. It will appear as lemma 8, 5, 15. Okay, so these variations and generalizations of induction principle we will have, and keep in mind that these are results. Okay, we have to, whatever we will state in these things, they have to be proved. Whereas the fifth axiom here is taken to be true. So that's why it's an axiom, it's an assumption. An assumption that we believe to be true, simply because it's so easy to see. Okay, now, right. Axioms 2.1 through 2.5 are known as the Peano axioms for the natural numbers. Right. So the 5 axioms we have introduced, they are known as the Peano axioms for the natural numbers. Now we will make an assumption. Since this assumption will involve again these axioms, so we number it according to how we have been numbering the axioms. Assumption 2.6. There exists a number system N which satisfies the Peano axioms. The elements of N are called natural numbers. Okay, you keep in mind that the 5 axioms we have introduced, they are in the form of some properties which we believe the natural numbers satisfy. Okay, and that is the assumption. So we are assuming that there exists a number system called the system of natural numbers, and whose elements are called the natural numbers, which satisfies the five Peano axioms. Now, why am I not calling this axiom? Because that is natural. No, I have introduced 5 axioms. So I am taking all of them together and making a single axiom. So I should have called this axiom, but instead I am calling it assumption. That's because here I have used the word elements, and a mention of the set of natural numbers is there. Since we have not introduced sets formally, so that's why this is still an assumption. When we will make this assumption more precise when we have laid out our axiomatic set theory in detail, and then this assumption will become an axiom in that axiomatic set theory. Axiomatic set theory has other axioms for set theory, just like we have Peano's axiom for natural numbers, there are axioms for set theory. Okay, and that treatment of sets is different from the thing we have already seen in naive set theory, and that takes care of that Russell's paradox and those things. So there, this assumption will become an axiom known as the axiom of infinity, because that axiom allows us to have a concrete example of an infinite set, namely the set of natural numbers. So that thing will come. So until that comes, we are simply calling it as an assumption. Now, it's a great achievement of analysis that using only these 5 axioms, 5 very primitive axioms, and the other axioms of axiomatic set theory, we can lay a foundation using which all other number systems can be constructed, and we can construct all the other functions and do our usual algebra and calculus the way we are used to. So that thing is there. So the base or the foundation of all our assumptions or axioms, in other words, that is not very complicated. But the thing which we can build using that foundation, that is enormous, and that is very far-reaching, and it's very satisfying to know that at the base level we have to consider only a few rules to be true, and everything else can be constructed based on that. Right. So this assumption, I forgot to put this word informal. That's because it uses sets, elements, those things which we have not introduced yet. Now there are some remarks regarding this whole thing that we have seen, the axioms, Peano's axioms. And these remarks are very important because they bring out different aspects of this development of the natural numbers. So this is the first remark. The usual order in which things are coming. So I had, before this item, I had proposition 2.1, 11. So this is Remark 2112. Now, whenever we say the system of natural numbers, look at this D. What does the assumption say? The assumption says that there exists a number system which satisfies the Peano axioms. The elements of this number system are called the natural numbers. So it only assumes the existence of at least one system of natural numbers, but it does not say anything about whether there can be more than one system of natural numbers. In fact, if you want to think of two different systems of natural numbers, you can think of it. Say you use the Hindu Arabic numerals, right? Which are the usual ones we encounter all the time, 0, 1, 2, 3, etc. Instead of that, someone may think of the Roman numerals. Strictly speaking, they are not the same thing. I mean, the symbols look different. Since the symbols are different, so strictly speaking, they are different. Now, in both the systems, the five axioms are satisfied in the usual way they are supposed to be satisfied, right? But we can make an association or a one-to-one correspondence. One-to-one correspondence. How? According to that, we will make the 0 of the Hindu Arabic system correspond to the 0 of the Roman system, which is O. And whenever any n in the Hindu Arabic system, any natural number n corresponds to a natural number m in the Roman system, the successor of n in the Hindu Arabic system must correspond to the successor of m in the Roman system. In other words, you see here 1 is what? The successor of 0, and I is what? The successor of O. So we will make them correspond to each other. Similarly, 2 is the successor of 1. Here I is the successor of I. So we will make them correspond, because here 1 and I are corresponding to each other. So that's why this. So according to this correspondence, so this correspondence we can say it like this. Corresponds the zeros of the two systems and preserves the incrementation operation in this sense, that whenever you have a correspondence between two quantities from the two systems, then their successors are also corresponding to each other. Okay. The technical term for this type of association is isomorphism. We will study isomorphisms properly when we get to algebra, modern algebra, where we see algebraic structures such as groups, rings, vector spaces. So there this idea will come. Okay, it will show up, and this is very important, far more important than the structures themselves. Okay, so now this is the thing, and because there is an association like this between any two natural number systems, okay, keep that in mind, between any two natural number systems, so you can see that whatever happens to one system, an exact replica of that thing happens in the other system. So essentially there is only one natural number system. There is no need to study this one separately while at the same time studying this one separately. Okay, they will produce identical results. So for the purposes of doing mathematics, one natural number system is enough. But we will actually prove this, and in one exercise we will prove that essentially there is only one natural number system. It's because here we have taken two concrete systems, right? The Hindu-Arabic one and the Roman one. However, if we are given two natural number systems arbitrarily, in what sense? In the sense that both of them satisfy the 5 Peano axioms, then we will show that there is such an association between the two, which will allow us to, it's like a dictionary which translates one word. If this is one language, this is another language. Okay, it translates one word from this language to the other language, and that translation, that scheme for that translation is the isomorphism. So this we will prove, and we will prove this. Let me see where we will prove this. Yeah, exercise 3.5.13, yes. The proof will look somewhat complicated, but once the proof is over, we can say for sure that essentially there is only one natural number system. Okay, so this was Remark 2.1.12 about the essential uniqueness of the system of natural numbers. This assumption says that such a system exists, and this exercise says that it's enough to consider only one such a system. There is no need to consider more than one natural number system. Okay. Now, so this was the 12th item. Then there are more remarks of this kind. Remark 2.1.13. Okay, so what this remark says, this is again informal. By now you know the meaning of this word informal, in what sense we are using it. So this remark says that the system of natural numbers consists of finite numbers. Every number in this system is finite. See, we have not defined what we mean by finite and infinite yet, but from the usual meaning of the word finite that we know from our English language, we can see that the numbers in this system are finite. However, the set of natural numbers is infinite. So if you think of the size of this set in the sense that the cardinalities of finite sets were introduced when we studied set theory, in that sense, if you think of the size of this set, that is infinity. If I just simply use the symbol for infinity. So while the set has elements which are individually finite, the set itself as an entity, it is infinite. So no natural number is infinite, but see, any natural number n is finite. N can approach infinity in the sense that it can grow larger and larger and larger. As a variable, n can grow larger and larger without bounds. So if you give me a very large natural number, okay, then I can make n larger than this, even this. By just adding 1, we can take this value for n. So this can happen, but at no point shall we have this. Okay, infinity is not a natural number. Infinity is not one of the natural numbers. This will never happen. So we have to keep this in mind while doing analysis, that while natural numbers can be as large as you want, none of them will ever be equal to infinity. Now there are some number systems which allow infinite numbers. Their elements themselves are infinite, either infinitely large or infinitely small but not zero. Okay, such systems are cardinals. In fact, we came across cardinality, but only of finite sets. Infinite sets also have cardinality, and there are different sizes of infinity. Okay, so this number system allows infinite numbers. Ordinals. This also allows infinite numbers. Cardinals and ordinals are somewhat similar, but cardinals are more in the sense of measuring the size of a set, and ordinals are more in the sense of labeling a sequence. It's somewhat like this. When we are considering finite numbers, there is almost no difference between them. So cardinals are 1, 2, 3, etc. Ordinals are also 1, 2, 3, etc. But cardinals are in the sense 1, 2, 3, whereas ordinals are in the sense first, second, third. So that order aspect is important. So that's why they are called ordinals. And there are other number systems also, p-adic numbers. So this sort of, which is something entirely different, okay? It depends on primes. So this sort of number systems allow infinite numbers, but none of them satisfies the axiom principle. Sorry, what the hell am I saying? The principle of mathematical induction, that is not satisfied by these numbers, and further study of these things is beyond the scope of these videos. If we get time at one point, we will have a look at them. They are very interesting, by the way. So this is another aspect of the system of natural numbers, that they can